Hello there. Welcome back to Calculus on the Go. So we're going to be diving into the concept of infinite series. And before we do that, I just want to kind of draw a parallel between the concept of a sequence and the concept of a series. So what is a sequence exactly? A sequence is just a set of numbers. It's a recursive set, meaning that the next number in the list depends on the previous one. This is one of the most conventional notation conventions we use. One of the most common notations we use for a sequence, a sub n, and then it could just be any number, a set of numbers. We could, for example, have 1, 2, my handwriting is pretty bad, 1, 2, and then 4, and then 8, 16, and so on. So in a set like this, it's pretty easy to decipher the code that we're using to create the sequence. We can tell what kind of a situation we have here. We can tell that every number is going to be twice as much as the previous one. So that's how we can kind of get a feel for what's really going on in a sequence like this one, like a sub n. And let's talk about what a series is. So a series is what we get when we add together the terms of a sequence. So a series starts with this Greek letter. It's a capital Greek letter sigma. Sigma always just means the sum. It means we're just adding together a bunch of things and getting a result. So in this class, we typically start with an index of 1. So I is the index. We're going to start with an index value of 1. And then we're going to be commonly going into infinity. And it doesn't make sense to add together an infinite number of numbers, does it? It seems like it would just never end. But this is kind of like the concept of an integral. So remember when we were first learning integrals, it didn't really make that much sense to have an infinite number of rectangles under a curve. It did not make sense to have more and more rectangles being added and then eventually getting the perfect area instead of just an estimate using a Riemann sum. But we found out using the limit that the limit is a really powerful tool, and it's actually the limit that helps us conceptualize the definite integral. It's the limit that helps us understand that it really is possible to find the area just by adding more and more rectangles to a curve, to the area under the curve, making them skinnier and skinnier rectangles, and then eventually we'll get the exact area, 100% correct. No longer an approximation, it's the real area. And that's kind of what this idea is centered on as well. The concept that we can make things smaller and smaller. And in some cases, we could say that a series could converge, kind of like an improper integral can converge or diverge. An infinite series is the same way. A series could converge, a series could diverge. So it's only possible to add together an infinite number of things if we can definitively prove if the series converges. If the series diverges, we have no chance of being able to find the sum. So this is, like I said, pretty similar to the improper integral chapter. In order to even integrate, remember that we had to verify, we had to be completely conclusive. We had to prove conclusively that the integral converged, because if it didn't converge, we couldn't take it. We couldn't find the improper integral, for example, going from 1 to infinity. It has to converge in order to do so, and then this is no different. In order for us to add together all the terms of an infinite series, we must prove conclusively that it converges first. If it diverges, we cannot add anything to anything. So I thought it would be really nice to come up with some examples and explore this concept of convergence and divergence and how it pertains to the infinite series. So this is a sequence. This is a series. Don't need that right now. Let's talk about one of the most common types of series. There's something called the geometric series. And it's pretty common. You may have seen this in Algebra 2. You may have seen this in pre-calc. It's pretty common. So an example of a geometric series would be just like one that I drew earlier, except that was a sequence. If we want to turn that geometric sequence into a geometric series, it involves adding all the terms together. So I like the numbers we had in the list. We had a 1, we had a 2, we had 4, 8, 16, 32, and so on. So the difference between a series and a sequence is that in a series, we're going to add together the elements in a sequence. This is our series. This is our geometric series. And if I wanted to stop right here, we call this a partial sum. We're not adding together an infinite number of terms. We're stopping after 5 terms. So we call this a partial sum whenever there's a finite number of elements in the series. This is a partial sum. So we're going to be not dealing with so many partial sums. We're going to be dealing with what happens as we add more and more and more. So we like to use a new kind of vocab convention when we're approaching topics like this. We like to introduce the topic of boundaries, or boundness, I guess maybe would be the proper word. It doesn't sound right, but I think it is right. Boundness, talking about if a sequence is bounded from above, and that is heavily related to the concept of convergence. So, whoops. Because we can see that the next one is bigger than the previous number, so 2 is bigger than 1, 4 is bigger than 2, 8 is bigger than 4, and so on. This is going to keep increasing without bound. So this would be divergent. This geometric series diverges, so we're not able to find the infinite series of this. But let's get into the main reason exactly why. We're going to get into the technical nitty-gritty algebraic reasons as to why this does not converge, as to why we cannot take the infinite series of this as x gets larger and larger. So let's see if we can create a recursive definition of the geometric series. So we know that in order to get to the next number, we have to double the existing number. That we call that the common ratio. The common ratio is just the number we multiply an element by to get the next element in the set. So it looks like we're just multiplying by 2 every single time. That means our common ratio has to be 2. And we use R as the identifier for the common ratio. Common ratio is 2. And then we have something else. We have the thing we're starting with. So the thing we're starting with in this case would be 1. So we have the identifier A being used to refer to our very first element in the set. So in this case, A would be 1. In this case, R would be 2. So because we are multiplying by R every single time, we could say that in order to jump ahead to a certain value, for example, what if we wanted to find A sub 5, or maybe even farther down the road? What if we wanted to find A sub 10, but we didn't want to find A sub 6 and A sub 7 and then A sub 8 and then A sub 9? What if we wanted to go straight to 10? We need a formula to do that. We need to create a formula that will allow us to go directly from the beginning all the way up to 10. So this is very symbolic and similar to what we've seen in algebra. This is similar to finding a rule, an algebraic rule. For example, if we have something like this. Oops, sorry. What if we have something like this, an XY table? And we're trying to create an expression that will tell us how X and Y are related. Typically we determine if it's linear, if it's quadratic, if it's exponential. And then depending on whatever kind of function it is, we would use the information we have available to us to create the expression or create the equation that would help us identify something that may not be on the table. What if we wanted to evaluate when X is 100 that's not on the table? We would have to create an expression and then just plug in X is 100 once we have the correct expression. And with sequences and series, it's very similar. We can express a sequence as an equation. So what we could do is let's write this series using the conventional series notation that we're used to. So we have Greek letter sigma, adding a bunch of things together. So we want to start, in this case, instead of I, the conventional notation for the index in a geometric series is going to be n. N is the notation for the index, so we're going to start with n equals 1. And then we're going to go to infinity. We're going to see if this converges or if it diverges. So let's see if we can get a good sense of what's really going on here. So it looks like we start with A. If we look at this very first term, notice how this is just A, nothing else, just A. And then what's after that is A times R. We have 2 up next, and notice how 2 is just A times R. And then what comes after that? We have our third element in the sum. This would be 4, which can be written as A times 2 times 2. That's 1 times 2 times 2. We could write that as AR to the second power, AR squared. And then further along that path, we have what's essentially just 1 times 2 times 2 times 2. That's what 8 is. 8 is just 1 times 2 times 2 times 2. So in other words, this is 1 times R to the third. And then from this point on, we have a pretty good sense of what's going on. We can tell that between every element in this sum, we're going to be just multiplying one multiple of r at every turn. So this would have to be a times r to the 4th power, and then it would just keep going from there. It would never end. So that's what this is all equal to. And then this would be a times r to the n minus 1. How do we know it's n minus 1 and not just n? The reason for that is because if we assign every one of these elements in the sum an index, if we assign every element an index of its own, like this, we want to ask ourselves what happens when we plug in an n value of 1. 1, 2, 3, 4, 5. These are all indices. They're all n values. So what happens when n is equal to 1? So we already know a is 1. We already know r is 2. So let's go ahead and plug things in and see what we get. So we have our a right there. We have our r right here. And then we have n minus 1. So in this case, we can see that n is 1. So n minus 1 is 1 minus 1. And see if we get the answer we're expecting. So actually, you know what? We might want to just leave this as a for now. So if we were to simplify this, our exponent turns into 0. We have 1 minus 1. That just says we have 2 to the 0 power. And then anything to the 0 power is 1. So 2 to the 0 power is 1. So what that means is that we really just have a times 1, so just a. And we want to make sure this is accurate. We want to make sure that this is truly the first element in the sum, and it looks like it is. So we tested this, and we got exactly what we expected, so we know we did it right. What if we didn't have n minus 1? What if we had just n? Then we would not get what we expected. If we had just if we had a times 2 to the 1st power, this would be 2a. And notice how we have just a as the first element and not 2a. So that's a really big indication that this is not correct. That's a really big indication that it has to be n minus 1 and not just the nth power. And again, that's just part of the really conventional notation for the kinds of things we're going to be doing in this chapter. This is extremely common to have things to the n minus 1 power. And you'll realize just how important it is to understand this when we get into something called alternating series and telescoping series. An alternating series is something that oscillates between positives and negatives. What if we wanted to turn this one into an alternating series? What if we wanted to make this minus AR plus AR squared minus AR cubed plus AR to the 4th and so on and so forth? The technical name for that kind of a series would be an alternating series. An alternating series can also converge and diverge in the same sense that a traditional geometric series can. We may or may not get into that in today's lesson. We'll see. We'll see how much time we have at the end of this part, and we'll see how things play out from there. So we have a recursive formula. We just tested it, and we've just decided that it works perfectly. It behaves exactly the way it behaves. It behaves the same way we expected to behave. Sorry, can't talk today apparently. So remember what we set out to do. We set out to see if the geometric series converges. We're trying to see if it converges or if it diverges. So like I said, the next part gets pretty technical, pretty nitty-gritty. We're going to need a lot of algebraic tools to help us make this connection between convergence and divergence of an infinite series, an infinite geometric series. So let's define S of n to be a partial sum. So for example, n would be the number of elements. So for example, if we have S of 3, that would be the first element plus the second element plus the third, and we would stop right there. So n is just the index that we stop on for whatever partial sum we end up with. So instead of using exact values, like here we used exact values, a and AR squared, with our definition, our formal definition of S of n, we want to be a bit more general. We don't want to be specific. We want to create something that can be applied to many different kinds of geometric series. Because to be honest, what we're doing right now, this is something that we're going to be using quite a bit between now and the very end of our class. this is something that's going to be used quite a bit, so it's a good idea to understand what's really going on here. So we know we have all of this stuff. The difference between this and what we have with S of n is that we're going to have an end. And it doesn't seem intuitive. I mean, we're going up to infinity. How is it even possible to write down the very last element? If we were going up to 1,000,000, it would make sense because we would have a ton of elements, but we still do have a clear, concise end. That would be 1,000,000. But with infinity, how the heck do we do that? How do we express in our typical math notation the very last element in an infinite number of elements, an infinite list of elements? So we're going to start with these first few elements we have, AR squared. And then depending on where we stop, we're going to end on A times R to the n minus 1. So we're just going to pick a value of R, or sorry, we're going to pick a value of n, and then this right here would be our very last element of the set. So now let's see if we can find R times S of n. So we already have S of n. So to find R times S of n, all we really need to do is multiply every single element by R. So we would get A times R plus A times R squared plus A times R to the third power plus dot, 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 plus we're no longer going to have an A times R to the n minus 1. This time it's just going to be an A minus R. Because if we multiply this by R, just turns into R, basically. Sorry, A times R to the n. I forgot to write the n. So our concluding element in this finite set would be A times R to the n power. So what's the point of that? What's the point of even finding R times S to sub n? It's important because we can go ahead and see if we can create a recursive formula for S of n. So notice how we don't have a formula for S of n. We just have a bunch of elements being added together. Let's see if we can create one for S of n. So we have, if we were to subtract these, if we were to do S of n minus R S of n, we would get something that looks kind of like this. So instead of having it lined up like this, I want to move things over a bit. I'm going to move everything over one space. And the reason why we want to do that is because now we can clearly see that a lot of these things just end up canceling each other out. And then what do we have left over? Well, we no longer have this A times R to the n minus 1 power. The only thing we have left would be this A and this minus A R to the n power. So if we were to express this product explicitly, whoops, we would have S of n minus R times S of n equals the only terms left over, which would be A, and then we distribute the minus sign, so this would be minus A sub A R to A times R to the n power. And again, I apologize for my really bad handwriting. I'm still using my on-the-go setup right now. I don't have access to my normal tools that I would usually use to teach this class. No drawing pad, no stylus, none of that. So I apologize if you have trouble reading my handwriting. So where do we go from here? We have this fact. We've proven that S of n minus R times S of n is A minus A times R to the n power. How do we solve for S of n? Let's go ahead and just add this to both sides of the equation. And what happens when we do that? We get Sn equals A minus R to the n. No, it's going to be plus R times S sub n. So this part goes away completely. And then from there, we can take out an R from both of these latter two terms. So we would have, actually, maybe we could start by taking out an A. Yeah, I think we should do that. But actually, before we do that, let's No, actually, yeah, I like this step. I think we should continue and factor out an a from the first two terms. So we would have a 1 minus r to the n power plus r times s of n. And then from there, we can express r times s of n as, whoops, give me a quick second. My apologies. So I feel like there might be a better way to go about this. So I want to leave that there. But I want to rewrite what we had originally. I want to rewrite this s of n minus r times s of n. There's a more efficient way to solve for s of n. So I want to factor out an s of n from both of these two terms. What we have left over is going to be just 1 minus r. And because I'm video recording this, I don't feel bad about erasing a bunch of things. If you need to go back and review some things, feel free. I want to keep this there. I want to move things up a little bit, give some more breathing room. Equals the very same. A minus a times r to the nth power. So I want to go ahead, I want to divide both sides of this equation by 1 minus r. When we divide both sides by 1 minus r, we get s of n equals a minus a r to the nth power. And then all of that divided by 1 minus r. And then what do we have? So let's see if we can simplify this a bit. So we know that clearly we're talking about infinite series. We're talking about n getting larger and larger and larger. We're talking about this variable n, the index. We're talking about the index approaching infinity. So what would happen to this expression if n were to theoretically reach infinity? So let's talk about what kind of a number r is, though, real quick before we continue. Why do we want to do that? Why is it important to understand what r is? How does that help us? So it's important to understand that because if r is within a certain range of values, it would make this whole thing behave so much differently than it would be for r to be part of another range of values. So what I mean by that is for this region, if we have -1 is less than r and r is less than 1, then r would have to be a fraction. R could be -1/2, could be -1/3, -1/4, -1 billionth, and then the same thing applies for positive fractions as well. It could be +1/2, +1/3, and then so on and so forth. So what would happen if we have, for example, r to the, what if we say theoretically that r is 1/3? And then this part right here, this part in the numerator, we have a times r to the n power. This would be a times r, which is just 1/3, 1/3 to the n power. So what happens as n gets larger and larger and larger? What value would it tend to? So 1/3 would just keep getting smaller and smaller and smaller. So as n approaches infinity, this whole thing would actually just approach 0. So that's why it's really important to understand what kind of a number r is. If r is 1/3, this whole thing approaches, this whole thing approaches 0. If r was a whole number, for example, what if r was 5? If r was 5 and n kept increasing, that means this whole thing would just keep continuously increase without bound. So we can only definitively prove convergence of an infinite series in this case if r is a fraction. So r has to be greater than -1 and less than +1. Otherwise, it definitively diverges. We can't do anything like that. We cannot find the sum. We can't do anything with that whatsoever. So we have to have r is between -1 and +1. And by the way, if I randomly go on pause, it's because I'm having an allergy attack. I probably sound pretty congested right now. Allergies are not being kind to me, so just a heads up. So we've already created a formal definition of s of n, depending on a and r and n. Now let's see if we can definitively prove that it converges. So far, the only thing that we've been able to do is prove that if r is greater than -1 and less than 1, it does not diverge. And notice how the fact that it does not diverge does not mean that it converges. I mean, maybe it does. I'm sorry. I guess I'm thinking of different words. That does mean it converges. So we have s of n. Let's see what happens if we take the limit as n approaches infinity. So we've already done that. N gets larger and larger and larger. Then this is going to just tend to 0. So the second term is just going to get smaller and smaller and smaller. So I want to take the numerator. I want to factor out a common factor of a from the two terms. We would have a times 1 minus r to the nth power, all divided by 1 minus r. So then what we would have is, actually, you know what? Sorry, I'm kind of all over the place this evening. I think I do want to keep it like this, but then I want to split it up into two separate fractions. So I want to put a over the denominator, and then I want to subtract the second term over the same denominator. So we're going to have a divided by 1 minus r, and then we're going to have minus a times r to the nth power over the very same denominator. So then from there, you may be wondering why we did that. The reason why we're doing that is to make things a bit simpler, because we've already proven that if n gets larger and larger, this whole thing would just tend to 0. And thus, we've simplified things quite a bit, which is a constant goal in mathematics. It's always a good idea to simplify things when possible to make it easier to get your answer and easier to interpret your answer, especially in situations like this where we have a big mess of variables and may be easy to lose track of where certain things came from, the significance of certain things. So simplification is always a really good tool to have on hand to help you find a solution and also interpret it. So far we have this, and we know that this whole thing is just going to become 0 as n tends to infinity. So we could say that the sum, what if we wanted to take the infinite sum of all these, the infinite series? We know this becomes 0. So what that means is that total sum is going to only be a divided by 1 minus r. So we've proved, not only did we prove convergence, but we also found a definitive formal definition of the sum of the geometric series, depending on a, which is the first element in the series, and also depending on r, which is the common ratio, which is the number that you multiply one element by to get the very next element in the list. So kind of cool. It was kind of a lot of work, but I feel like it was worth it to understand just how these types of problems work and just to understand where these definitions of rigidity come from, the definitions we use for convergence and divergence, and how to find the sum of something like this. It's important to know where this comes from. It's important to have at least a basic understanding of how we derive things like this. So what comes next? Oh, we want to add a condition. So we note that this only converges if r falls within a certain value. But let's take it a step further. Let's, instead of making it negative, r has to be between -1 and +1, let's make it a little more simple. Let's say the absolute value of r has to be less than 1. So this includes only positive values of r that are less than 1. So basically, it includes all proper fractions between 0 and 1 for this sum to actually have a definitive value. For example, like I said before, if r is, for example, 5, if r is 5, this does not apply. It only applies when r, the absolute value of r, is less than 1. So now that we have a nice little formula that helps us find the sum of an infinite geometric series, I feel like we should start with some examples to help us hammer in this idea a little bit further, to help us understand a little bit more. An example is a really great tool for understanding a concept even further. Let's say we have the following geometric series. Let's say we have a sub n. Well, in this case, it's a sequence. But we're going to convert this sequence into a series. So we have a sub n is the sequence of 5 minus 10 over 3 plus 20 over 9 minus 40 over 27, and so on and so forth. So we want to find the sum. And in order to find the sum, if it's even possible to find the sum, we have to definitively prove that absolute value of r is less than 1. Common ratio has to be between -1 and 1, or we can also think of that as being the absolute value of the common ratio must be between 0 and 1. So how the heck do we prove that? So remember what r really represents. Remember what the common ratio really means in this context. So a common ratio is the number we use to get the next element in the set. So if we start with a number, multiply it by a common ratio, we get the next number. So let's start by factoring out a 5, because we can see that we have 5 would be the first element, and then we double that, we get 10, and then we double it again, and then we double that again. So let's factor out a 5 from everything out of these first 4 terms. We'd have 1 minus 2/3 plus this would be 4/9 minus 8 over 27, and so on. So now that we factored out the thing they have in common, let's see what number we have to multiply by to get the next element in the set. So 1 times 2/3 is 2/3. 2/3 times 2/3 is 4/9. 4/9 times 2/3 is 8/27. So we're almost there. The only thing we have left to worry about is to contend with the negative signs. If they were all positive, things would be a bit easier. But we have to take into account that this oscillates between positive and negative values. So in general, we want to learn how to create a mathematical tool that we can add to this recursive rule that we're building right now that would take into account that every odd element has to be positive. So we have 1, 2, 3, 4 of these are our indices. So whenever we have an odd index, it produces positive elements. Whenever we have even indices, it produces negative elements. So in this case, this is actually going to be negative 2/3. So the common ratio has to be a negative number. It has to be negative 2/3. And A is pretty easy to see. Pretty easy to see that the first element of the set is 5. So A has to be 5. So now that we know, well, actually, we don't know quite yet if we're able to add these things together infinitely. So let's see if we can make sure that this holds true. Make sure that the absolute value of r is less than positive 1. So absolute value of r is equal to positive 2/3. And positive 2/3 is absolutely less than 1. So this rule is being upheld. And because the rule is being upheld, we can definitely prove that this thing converges and that we are able to take the sum. We can only take the sum if this condition is being held true, which it is. So let's find the sum. So the sum, S of n, that's just the shorthand we use, notation. It would be A, which is 5, over 1 minus r. So that would be r minus 1 minus negative 2/3, which is 1 plus 2/3. And then we can think of 1 as just being 3/3. So this is like saying we have 3/3 plus 2/3, which would be 5/3. So we have 5 over 5/3, which is equivalent to 3. So if we were to add together an infinite number of elements in the set, we would eventually get to 3. And this is one of the more beautiful things about math. You would think something like this, that gets pretty complicated pretty quickly, gets into some nasty looking fractions, you would think it would be some nasty number as the final result if we add together an infinite number of terms. You would think maybe it's some decimal or some something that doesn't terminate, but it's actually just 3. I know it's mind-blowing. My mind is blown too. But it is just 3. If we were to add together an infinite number of terms in this geometric infinite series, we would get just 3. So now we're going to be talking about something called a test for divergence. And this is something that can be applied to a lot of different types of infinite series. And it is a really powerful mathematical tool to have in our arsenal to help us solve complex problems down the road. So, and that is the formal name for it, just test for convergence. Sorry, test for divergence. So it goes something like this. If the limit as if the limit as n approaches infinity, does not exist, D and E is does not exist, or if it equals something that's not 0. Then that means that the series diverges. And I'm sorry, I meant to put something there. I meant to make this the limit as n goes to infinity of the sequence a sub n. And then same thing down below. So if either of these are true, then the series diverges. So let's put this into practice. Let's take a fairly complicated series and use this test for divergence and see if we can definitively prove if it converges or diverges. So we have the sum starting with n equals 1, going to infinity, of n to the second power, all over 5n squared plus 4. So we want to take this test for divergence and see if it applies in this situation. So we want to take the limit as n approaches infinity of our sequence. N approaches infinity, n squared divided by 5n squared plus 4. So what we can do now is we can take this n squared and then we can factor out an n squared from all 3 of our terms. We have 1 term on top, we have 2 terms on the bottom for a total of 3 terms. Let's factor out an n squared from all of those terms. When we do that, we have just a 1 left over on the numerator. Down below, we would have just a 5 left over, plus if we divide 4 by n minus 1, or sorry, 4 by n squared, we would just get this, 5 plus 4 over n squared. And it's useful because it's much easier to decipher a limit, to tell if the limit exists, and if it does exist, what the value of the limit is. If we have only one variable to worry about, it makes things considerably easier and faster for us. So this is just going to be 1, goes away, it loses significance. So what happens as n tends to infinity? So this part right here would just approach 0. So n would get larger and larger and larger. The ultimate value of this part of the denominator would just go to 0 eventually. And what are we left with? We're left with 1 over 5 plus 0. So we're left with just 1/5. And we have our answer. So let's go take a look at the test for convergence and see if it diverges. So this first condition does not apply. First condition applies when the limit does not exist. Clearly, our limit does exist. Our limit has a value of 1/5. So the first condition does not apply for this particular problem. The next one does. It says it also diverges if the limit does not equal 0. And this applies perfectly to our situation. Our limit does not equal 0. Our limit is 1/5. So that's how we know that this diverges, because we took the limit and we did not get 0. So we're 100% sure that this thing definitely diverges. So I highly recommend you put this in your notes if you haven't already. It's a really useful tool to have at your disposal. So let's talk about finding the sums of different types of geometric series. And remember that first, if we even want to take the sum, we have to prove that it converges. If it converges, we can do it. If it diverges, we cannot take the sum of an infinite geometric series. Let's say we have the series going from I equals, sorry, I'm so used to using I instead of n. Starting with n equals 1, going up to infinity. And then we have this expression. We have 3 divided by n times n plus 1. Plus 1 over 2 to the n. So we want to see if we can identify a common difference in the first term. So let's ask ourselves, well, let's find A. A is the first term in the sequence, the first element of the set. R is the common difference. We can find both of those things. So let's plug in an index of 1. So if we plug in n is equal to 1, we get 3 divided by 1 times 1 plus 1. 1 times 2, so this would just become 3 halves. And then this thing over here would be 1 divided by 2 to the first power. That would just be 1 half. 3 halves plus 1 half is just 2. So we have our first element of the set. So whenever n is 1, this whole thing in parentheses has a value of 2. That is our first element in the set. That is the first term in the sum, first term in the series. Now let's see if we can find the common ratio between terms. So let's see what happens when we plug in n is 2. So if n is 2, the thing in parentheses becomes 3 over 2 times 2 plus 1 plus 1 over 2 to the second power. Now let's simplify. So we would have, well, 2 plus 1 is 3. We have a 3 on the bottom and we have a 3 on top. They cancel away, leaving us with just 1 half. And then this would be 1/4. We have 1 half plus 1/4. And I apologize for that. I got a bit too eager. I dived right in when we were really only supposed to deal with these term by term. So let's just deal with this 1 divided by 2 to the nth power. So whenever n is 1, our starting term is going to have to be 1 half. If we plug in 2, we get 1/4. So we can see that the common difference, or the common ratio, I mean, R, is also going to have to be 1 half. So A and R are both 1 half. So let's see if we can split this up and then determine what the separate parts add up to. So I want to write this as the infinite series, n equals 1 to infinity. Of our first term, this would be 3 divided by n times n plus 1. And then we're just going to add the other part. So we're dealing with this part right now. We have 1 divided by 2 to the nth power. We have an A value, we have an R value, which means that we can use our definition we had earlier to determine the sum of this part of our infinite series. Remember, it's just going to be A over 1 minus R. So this part right here, we know A is 1 half. We have R is also 1 half, so this 1 over 1 minus R would be 1 minus 1 half. So this equals 1. So this entire infinite series just equals 1. Now let's see if we can do the same thing for the other part. So we can start by taking the 3 and moving the 3 outside. That is something that we're constantly able to do with integrals and limits and derivatives and things like this. A constant like that can always be moved to the outside of the operator. And now we have 1 over n times n plus 1. And this just turns into 1. So whenever we have something like this is one of these you're going to just want to remember. Whenever we have 1 divided by n times the product, or sorry, n times the sum of n plus 1, this whole thing in the box is just equal to 1, which means this whole thing is equal to just 3 in that case. So this infinite series we have, we split it up into 2 separate series, sub-series if you will. We found out that the first one is equal to 3. We found out that the second is equal to 1. So that means the entirety of all of this, starting at an n value of 1 and taking larger and larger values of n as n approaches infinity, would have a total sum of just 4. So I feel like now is a pretty good time to maybe stop for tonight. It's kind of a lot of information to take in. So again, I'm sorry about the irregularity with which I'm recording these videos. Things are going pretty crazy in my life right now, and a lot of traveling, a lot of unexpected things popping up. So I appreciate your patience while we grind through this last calculus on the go part of our class. And definitely please let me know by email if you have any questions about anything. If you want specific videos explaining specific topics, I'd be more than happy to do that for you. So in that case, have a wonderful evening. I'll see you next time. Bye.